Let's look at an example of using iteration to compute something interesting. We're going to compute elements of the Fibonacci sequence. Here's Fibonacci, a mathematician from long, long ago. And here's his sequence. Actually, this sequence was described long before Fibonacci found it, but he's the one who made it popular in the West. So we talk about him every time we see this sequence of numbers, which starts with 0, then 1. And then each element after that is the sum of the previous two. We usually call this the 0th element, this the first, this the second, and this the third. Now, Fibonacci numbers have lots of wonderful properties. One cool thing you can do is tile together squares where the side lengths are Fibonacci numbers. 1, 1, 2, 3, 5, 8, etc. And you get this very nice looking spiral called the golden spiral. People seem to like to look for that in nature. Here's a picture of a cabbage. How might we compute these Fibonacci numbers? Well, here's one option. We'll use a function with a while statement that just works its way up the sequence. So we start out by saying that the preceding and the current Fibonacci numbers are 0 and 1. And k equals 1 means that Kerr, the name, is bound to the first Fibonacci number. This one. That's the 0th. That's the first. Okay. While k is less than n, we need to advance our way up the sequence. And we can do that by rebinding pred and Kerr to Kerr and then pred plus Kerr. Here's the part where we're saying the next Fibonacci number is the sum of the current one and its predecessor. And then we also increment k to say we've moved our way up the sequence. When that while statement is finished, we can return the current Fibonacci number, which is the kth one, where k is now n. In the environment diagram, we'll have pred and Kerr bound to 0 and 1 at the beginning, and then every time we execute this assignment statement, we'll rebind pred and Kerr to be two numbers farther up, always next to each other, but farther up in the Fibonacci sequence. So now they're 1 and 1, now they're 1 and 2, now they're 2 and 3, now they're 3 and 5. And in this way, we can compute any Fibonacci number we want just by letting that while statement run as long as we care. Okay, so here's a discussion question for you to think about. I've defined a function pyramid, which counts its way up and down. So a starts out at 0, b starts out at n, and then while b, we rebind a and b, and we increase total in some way. Then we return total. This example is courtesy of my wife, who likes to do pyramids of push-ups. 1 push-up, then 2, then 3, then 4, then 5, then 4, then 3, then 2, then 1. Anyway, the question is, for this function definition, what does pyramid n compute? Does it compute n squared, or n plus 1 squared, or 2 times n plus 1, or n squared plus 1, or n times n plus 1? Think about it for a second. Well, here's one way to visualize what you get. A is going to be increasing and b decreasing. So let's say we pass in n is 4. Then the first time that we add to total, a has been increased to 1 and b has been decreased to 3. And then we add to total again, where a's gotten bigger and b smaller, a gets bigger again and b smaller, and finally, a is 4 and b is 0, at which point we're done. So what happened here? Well, we computed 4 squared. So the answer is n squared. Another way to see that is that we're always adding a and b together, and that sum never changes, because we always add 1 to a and take 1 from b. So the total a plus b is always what it was before. Originally, it was n, and we execute this while statement body n times, so n times n is n squared.